Okay, what if some of the most fundamental shapes we know, like triangles, held a sort of hidden mathematical secret? A characteristic may be so precise, so unique, that it only really shows its complexity when you start looking at them. Not one by one, but by the millions. Today, we're taking a deep dive into exactly that kind of fascinating territory. Our topic, what mathematicians call fortunate triangles. And our ultimate quest, well, it's to unravel a truly monumental numerical puzzle, finding the value of S107. It's a journey that blends elegant geometry with the sheer scale of number theory.
That's right. And for this exploration, we're actually drawing from some pretty captivating source material. We've got this remarkable diagram, as it's called, which visually anchors these concepts. And we also have excerpts from a paper aptly titled Fortunate Triangles, Orthocenter and Circumcenter Distances. So this isn't just, a theoretical exercise. It's really a peek into how a very specific geometric definition can sort of blossom into this colossal computational problem.
Right. So let's start at the beginning then. What exactly defines a fortunate triangle? The first criterion is pretty straightforward. They must have integral sides.
Yeah, integral sides, that just means their side lengths are whole numbers, no fractions, no decimals, easy enough.
Like a classic 3, 4, 5 triangle, maybe. Or that 6, 7, 8 example we'll get into.
Exactly. Simple whole numbers.
But that's just let's say, the entry ticket. Here's where it gets really unique, mathematically quite elegant, I think. A fortunate triangle has this very specific geometric condition. It involves two special points within any triangle. Its orthocenter and its circumcenter.
Right. And many of you probably remember these from geometry. The orthocenter, usually called H, that's where the triangle's altitudes intersect, right?
Mm-hmm.
The lines drawn from each vertex perpendicular to the opposite side. And the circumcenter, that's the center of the circle that passes perfectly through all three vertices of the triangle. They're fundamental points in triangle geometry. But what's really captivating about fortunate triangles isn't just that these points exist, it's this highly specific, almost, elegant 1-to-2 distance ratio that defines them.
A 1-to-2 ratio.
Exactly. Specifically, a triangle is fortunate if, for at least one of its vertices, the distance from that vertex to its orthocenter, H, is exactly half the distance from that same vertex to its circumcenter.
It's this particular relationship, yeah. It comes from this subtle interplay of altitudes and perpendicular bisectors. That's what makes these triangles mathematically special. It's like a numerical lock on a geometric shape, a really nice convergence.
That's a great way to put it, a numerical lock. It's not just any relationship, like you said, it's this precise half-distance rule. And to make it really concrete, our source material gives us a perfect example, a triangle with sides, 6, 7, 8. This one is explicitly called out as a fortunate triangle. Yes, and the numbers provided in the source material really spell it out clearly. If we look at vertex C in that 6, 7, 8 triangle, the distance from C to its circumcenter, O, is calculated as approximately 4.131182.
Okay.
Now, the distance from that very same vertex C to its orthocenter, H, is approximately 2.065591.
Ah, I see where this is going.
Right. You compare those two values, and 2.065591 is, exactly half of 4.131182. Bang on. So that confirms 6, 7, 7, 8, 8 as a fortunate triangle. And that remarkable diagram we mentioned, it really helps visualize this. You can actually see vertex C and then O and H plotted. And the segment from C to H looks visibly shorter, about half the length of the segment from C to O. It makes a kind of abstract definition feel quite tangible.
It certainly does. You can almost picture the geometry locking into place there. Okay, so we sort of nailed down what makes a single triangle fortunate. But as you hinted earlier, the real challenge, the deep dive into these shapes, isn't just about finding one or two. It's about how they behave, together.
Yeah.
How they contribute to a larger mathematical picture. And that's where this function ST comes into play.
Exactly. We're shifting gears now from looking at individual instances to understanding a collective property, a summation.
Right, so SP is defined as the sum of A plus B plus C, which is just the perimeter, obviously, over all fortunate triangles. But there are a couple of key conditions. The sides A, B, and C must be ordered, usually non-decreasing, so A, B, A, C. And critically, the triangle's total perimeter must not exceed P. So essentially, we're summing up the perimeters of all the fortunate triangles that fit within a certain size limit, P. It's about finding every single one that meets the geometric condition and the size constraint.
And this is where that initial, seemingly simple definition starts to show its underlying complexity, doesn't it? Because you're not just finding the fortunate triangles, you then have to sum their perimeters, which means you need a way to find all of them within that perimeter limit piece, systematically.
Yeah, exactly. The source material actually gives us some specific, smaller examples of SP to help illustrate how it works. For instance, it tells us that for S10, the value is 24.
And that value, 24, for S10, it comes from 3 distinct fortunate triangles whose perimeters are 10 or less. Those triangles are 1, 2, 2, 2, 3, 4, and 2, 4, 4, if you just add up their sides.
Okay, let's see. 1 plus 2 plus 2 is 5.
Right, and 2 plus 3 plus 4 is 9.
And 2 plus 4 plus 4 is 10.
Yep. So you sum those perimeters, 5 plus 9 plus 10, and that gets you precisely 24. So it's not just some abstract formula. It's a very tangible sum, built piece by piece from these specific geometric shapes that meet the criteria. It's a neat example of how these definitions lead to concrete numerical results.
It is. And then the source makes quite a jump. It notes that S100 equals 3331. Wow, that's a big increase from just 24.
It truly is a big leap. And if we think about the bigger picture here, that jump from S10 being 24, which came from just 3 triangles, not S100 being 3331, well, it strongly suggests that the number of fortunate triangles grows really rapidly as the perimeter limit P increases. It's definitely not a simple linear increase. It points towards a rich and probably incredibly complex distribution of these special shapes hidden within the vast set of all possible integer-sided triangles. This kind of growth really highlights the combinatorial nature of the problem. Even a modest increase in P seems to unlock a vastly larger set of triangles that qualify. Finding them all becomes a serious task.
And that rapid, maybe even exponential-like increase brings us right to the heart of it, the grand challenge, the core of this deep dive.
Yeah.
The task to find S107. Let's just pause for a second on the scale of 107. That's 10 million. Think about it. Our examples were S10 and S100. Finding S107? This isn't just a slightly bigger number. It's a truly monumental leap in complexity. We're talking about finding all fortunate triangles whose perimeters don't exceed 10 million and then summing all those perimeters. This isn't something you can tackle with pencil and paper, right? Or even a basic computer program, I imagine. It moves squarely into the realm of significant computational challenges.
Absolutely. And it immediately raises that critical question. How on earth do you even start to approach finding S107? It's crystal clear from that huge jump in scale that you can't just draw diagrams or list triangles by hand. Like you said, forget it. You couldn't possibly check, potentially billions of triangle combinations up to a perimeter of 10 million and test each one for this fortunate property individually. It's just not feasible. So this points directly towards the absolute necessity of using advanced mathematical principles and almost certainly highly sophisticated computational approaches. We're likely talking about clever algorithms, maybe number theoretic sieves, insights from computational geometry, things designed to systematically identify only the qualifying fortunate triangles without checking every single possibility. It demands really optimized methods to handle that enormous search space.
That's where the real insight of this problem seems to lie, doesn't it? It perfectly exemplifies this progression you see in mathematical problems. You start with an elegant, maybe even simple-sounding definition, like our fortunate triangle rule. Then you explore what that definition means when applied across vast data sets or possibilities. And just as we're discussing, that exploration often forces the development of entirely new methods, new algorithms, and relies heavily on computational power to actually find the answer. It's this perfect blend of theoretical beauty, the specific 1-to-2 geometric ratio, and the hard-nosed reality of computation. It forces us to ask, how do we efficiently sift through potentially billions of candidates to find just the ones that fit this very specific, delicate criterion?
It really does. And I think the true insight here isn't just about the sheer scale, although that's impressive. It's how this problem fundamentally forces us to grapple with the delicate interplay between these seemingly abstract geometric conditions and the brute force reality of number theory. It's not just about calculating a sum. It's about potentially discovering new shortcuts, new mathematical structures, new ways of thinking about how shape and number are fundamentally intertwined, especially under these very specific constraints. Knowledge is most valuable when it's understood and applied. And problems like this one really stretch our understanding of what's computationally feasible and what's mathematically discernible. It pushes boundaries.
So, digging into this, why should you, our listener, care about finding S107 or the properties of these fortunate triangles? Well, beyond the immediate mathematical puzzle, which is fascinating in itself, this kind of challenge illustrates a much broader point, I think. It shows how these fundamental definitions, sometimes seemingly simple ones, can unlock entire fields of inquiry and demand incredibly sophisticated problem-solving strategies. It's really about how we systematically search for and categorize specific structures within vast sets of numbers and shapes. That makes you think, doesn't it? About how we model and explore complex systems in general, whether it's in pure math, computer science, or even in fields like, say, data analysis, where you're constantly trying to find very specific, maybe rare patterns in a huge ocean of information.
Absolutely. This kind of problem really encourages us to think critically about how we find patterns, how we identify specific characteristics in large sets of data, even when those data points are geometric shapes defined by somewhat abstract properties. It's about more than just getting the final number for S1 or 7. It's about the journey of discovery, the development of new methods, the push for computational efficiency that's required to navigate such an expansive mathematical landscape. It really highlights that often the most profound insights emerge when we combine different branches of mathematics, letting geometry inform number theory, and letting number theory provide tools to explore geometric questions on a grand scale.
And there you have it, our deep dive into the intriguing world of fortunate triangles. We've journeyed from understanding their unique, precise definition involving that 1-to-2 ratio, explored how the SP function aggregates them by summing their perimeters, and really tried to grasp the massive computational challenge posed by finding S107. It's a great reminder that even in fields as ancient as geometry, there are still these fascinating complex secrets waiting to be unearthed, especially when you start looking at scale.
It definitely reinforces that idea that within seemingly simple definitions, these complex and fascinating mathematical worlds exist, just waiting to be explored. And often, like here, it's the sheer scale of the problem going up to 10 million that reveals the true depth of those worlds and pushes the boundaries of what we can actually compute and understand.
Indeed. So as final thought for you to ponder, consider how these quite abstract geometric properties, when you combine them with specific numerical conditions like integrality and perimeter limits, can lead to such grand computational challenges. What other fortunate or special hidden structures might be out there, waiting to be discovered and explored? Perhaps in fields you might not even expect, just by looking at definitions a little differently and being willing to explore them at a truly massive scale.